Welcome to this Rapid Fire Explainer. We've got a really fun challenge today. We are going to definitively and mathematically prove that a mass spring system executes simple harmonic motion. And we're going to do it in just about 2 minutes. So we aren't just skimming the concepts here, right? We're actually diving into the exact mathematical collision that proves the physics. Let's start the clock.
What is the mathematical finish line to prove a system is executing simple harmonic motion? Okay, to start, we need to know what we're actually aiming for. In physics, it's never enough to just look at an object bouncing back and forth and call it a day. We need hard proof. So, what's the ultimate finish line we have to cross to definitively prove a system is executing simple harmonic motion, or, SHM for short? Well, we have to hit a very specific set of conditions.
Condition for SHM, acceleration, or A, must be directly proportional to negative displacement, or negative x. So, here is the strict definition of the motion itself. For any object to actually be in simple harmonic motion, its acceleration must be directly proportional to its displacement from the equilibrium position. But hold on. Notice that negative sign in there? It's literally the most important part. The acceleration is directly proportional to negative displacement. That little minus sign tells us that the restoring force, and therefore the acceleration, is always pointing back toward the middle, the equilibrium position. Basically, if the mass moves to the right, the acceleration pulls it back to the left. If we can mathematically arrive at A is proportional to negative x, boom, we cross the finish line. That's the exact target we have to hit.
Okay, picture the physical setup in your head. We've got a block with a mass of m, and it's hooked up to one end of a nice, bouncy elastic spring. Crucially here, this block is resting on a perfectly frictionless horizontal surface. So, when the block is just sitting there completely still, it's at its happy place, the equilibrium position. But the second we pull or push that block away by a distance of x, the elastic restoring force of the spring kicks in, trying to pull the block right back to that center point. Now, every spring is a bit different, right? The force required to stretch or compress it is determined by its stiffness. In physics, we call that the spring constant, or K.
Now here is where it gets really interesting. We can actually define that restoring force using two totally separate, legendary rules of physics. On one hand, we've got the spring's perspective, which is Hooke's law. For an ideal spring, the elastic restoring force, let's call it F-res, is directly proportional to the displacement, x. And because the force and displacement are fighting each other in opposite directions, we get that vital negative sign again. So, F-res equals negative k times x. On the other hand, we have the mass's perspective, courtesy of Newton's second law of motion. The restoring force creates an acceleration in our block, giving us F-res equals mass times acceleration, or m times a. It's pretty cool when you think about it. Two totally different laws describing the exact same restoring force.
So let's smash them together and watch this equation collision happen. Step 1. Since both of those equations equal F-res, we just set them equal to each other. So m times a equals negative k times x. Step 2. We need to isolate acceleration, a, because remember, that's what our finish line requires. If we just divide both sides by m, we get a equals negative k divided by m, all multiplied by x. Now for the final piece to the puzzle. Step 3. Think about this. During the entire oscillation of this mass on the spring, does the mass m ever change? Nope. Does the spring constant k change? No way. They're constants. So since k over m is just a fixed constant value, we can drop it entirely to reveal the underlying proportionality. And what are we left with? Acceleration a is directly proportional to negative x. Boom! We literally just crossed the finish line. We proved, without a doubt, that the mass spring system executes simple harmonic motion, and we did it in under 2 minutes.
This incredible mathematical predictability is exactly why physics is just so powerful. We can distill the seemingly complex physical movement of a bouncing spring down to one simple, elegant proportional rule. But it does leave us with a pretty fascinating question to ponder. What if we change the system entirely? Like, if we completely remove the spring, suspend a mass from a string instead, and just let gravity provide the restoring force? Does a swinging, simple pendulum follow this exact same mathematical rule? Think about that for a bit, and we'll see you in the next explainer.